Good morning, everybody, and welcome to the first online engagement session of today's program. My name is Jenny Hogan. I'm the Outreach Manager for the Centre for Quantum Technologies here in Singapore, and we'd like to thank NRF for inviting us to participate here with you today at the Global Young Scientist Summit. So we're very lucky to have with us this morning Prof. Loh Huanqian, who's going to talk to you in just a moment about quantum computing. First, I'm going to give you a little context on the Centre for Quantum Technologies, which we call CQT for short. So CQT was established back in 2007 as Singapore's first research centre of excellence. We're now 15 years old. We have some 230 staff and students who do research across 3 application areas of quantum technologies. So that's computing and simulation, communications and sensing and metrology, as well as developing advanced instruments and continuing with curiosity-driven basic science. We're hosted at the National University of Singapore, but we have researchers too at the Nanyang Technological University and with the Agency for Science, Technology and Research. So many of you in the audience may know about quantum technologies. It's a very fast-growing field around the world. And here in 2022 in Singapore, they've established a national quantum office that will be guiding the country's national strategy, and CQT will be supporting this effort to grow the research and industry ecosystem here. So we already have a few quantum startups even here in Singapore that are founded by our alumni. But I think we should get to the science. So our research is led by 25 principal investigators, and Prof. Loh is one of them. Huanqian's also a President's Assistant Professor appointed in the NUS Department of Physics. And for her research, she's been recognized as an NRF Fellow in the class of 2018. And in 2020, she was named as one of 15 of L'Oreal UNESCO's International Rising Talents worldwide. She's also serving on the World Economic Forum Global Future Council for Quantum Computing. So she'd started her research career as a PhD student in the US in the lab of Nobel laureate Eric Cornell, and now she's leading her own group here in Singapore. So those of you participating in GYSS, you can ask questions during the talk by typing them into Slido, and we'll be keeping an eye out at the end. So Huanqian, I'd like to pass over to you.
Okay, thanks Jenny for the introduction, and thanks to NRF for the invitation to give a short talk here. Today I'm very excited to share with everyone some of these basic ideas on quantum computing. And then I plan to run through one of the leading quantum computing platforms, which is with these arrays of neutral atoms. That is also the platform that I work with in my laboratory here at the Centre for Quantum Technologies in the National University of Singapore. So this is supposed to be a fairly short talk, and I look forward to having lots of questions from everyone. So let's go to the very basics. In classical computing, we encode data using bits of zeros and ones. Now, in quantum computing, we also use strings of bits, but each of these bits can behave like a quantum bit, or what we call a qubit. Right? So a qubit can be in state 0, or it can be in state 1, or it can be in both at the same time. So now, quantum mechanics describes basically the world of the very small, or the very cold. So suppose, let's imagine you have atoms as your qubits. So you may have noticed that here I indicated the state 0 as this atom being in the lower state of 2 states. Or this atom can be described as behaving like a little magnet that points upwards. In any case, either of these pictures works just fine. And the idea, once again, is that this qubit can be in both states at once, or what we call a superposition of both states. On the other hand, the power of quantum computing doesn't come from having just a single atom being in a superposition state. Rather, this power comes from having many atoms that can be put in some collectively entangled state. Now, this entanglement is a funny thing. If you have 2 particles that are highly entangled with each other, it means that the moment you measure the state of one particle, you immediately know the state of the other particle with a much higher degree of correlation than you can ever explain classically. So what is this quantum computing good for? Well, some of the famous examples include trying to factorize large numbers, which is of course important for breaking today's RSA keys, or you can have a more efficient search algorithm. And the governments recognize the power of having such quantum computers, which is why today there is really extensive effort in many countries around the world to pursue quantum computing research as a strategic trust. However, quantum computers that can perform such tasks are not yet on the horizon, because in order to do so, you require millions of qubits that can perform these gate operations pristinely, which means at a much lower error rate than what can currently be achieved. In fact, one would say that today we are living in the NISQ era, which means that quantum computers today are these noisy intermediate scale quantum devices. Okay, so they are noisy and they are not that large yet, but somehow even when we have these NISQ devices, there has been tremendous interest, even from industry, to jump onto quantum computing research. So here's a list of some of the companies that are involved in quantum computing. Of course, you've got the big tech companies, to those that are in the transport, energy, and finance sector, to startups that pursue quantum computing, including, of course, some of our very own spin-offs here in Singapore of CQT. So there must be interesting problems that can be solved by these NISQ devices, and that is what I want to focus for the rest of this talk. So to appreciate the kinds of problems that are tackled by these NISQ devices, let's take a different approach. So we'll take a look instead at the problems that take up the most computing resources of these classical supercomputers today. Now here's a pie chart of one of these supercomputing centers, for example. And many of those problems, as you can see here, are materials research and chemistry problems with some engineering and various optimization problems involved here. And so what happens with these classical simulations, right, is that you have very clever theorists who come along and write down a model of the problem that is to be solved, input those equations into a supercomputer, which then spits out the results after some time. However, some of these challenges require solving quantum mechanical problems, which are notoriously hard to calculate. For instance, if you want to exactly solve for the time-dependent behavior of a collection of even a few hundred atoms that are strongly entangled with each other. That can be a very challenging problem because the number of classical bits that are required to completely, exactly model this system would be more than the number of particles you have in the whole universe. Okay, so that's a problem. And the solution to this problem can be found in these quantum simulators, which are what many of these NISQ devices can act as. So there's a famous physicist, a Nobel laureate himself, Richard Feynman, who once said that nature isn't classical, right? So if you want to make a simulation of nature, you had better make it quantum mechanical. By golly, that's a wonderful problem because it doesn't look so easy. So the idea here is to use this simple quantum nanomachines, right, the NISQ devices. And these are physically like atoms, molecules, photons, which are particles of light. You use them to simulate more complex quantum phenomena. And Feynman is right that it's not so easy, right? Because these simulators need to be controlled, isolated, and yet tunable. However, once you can set up these simulators to obey the same equations, right, as those that model the complex phenomena, then you can simply perform your analog simulation by letting your atoms or molecules evolve in time. And then you can read out the answer by making measurements on the states of your atoms or molecules. Now, to see how quantum simulators work, let's consider materials as an example. Right, so in general, the macroscopic properties of materials map onto the microscopic behavior. So for instance, electrical conductivity is simply related to how charges, electrons, move in time, and thermal conductivity is related to how phonons move in time. So if I'm allowed to now think of materials as a collection of atoms, right, they are arranged in a particular underlying geometry, and if I can induce tunable interactions between them, then I can dream of building up these analog materials with my quantum simulators as these Lego blocks. And these are built up block by block. And then the dynamics of these Lego blocks are then related to the macroscopic phenomena that I mentioned earlier on. So here is actually a list of some of the very promising candidate platforms for quantum simulation and eventually for quantum computing. So you've got trapped ions, superconducting circuits as two of the big candidates. And of course, you've got optical lattices, quantum gases, photons, and so on. Now, each of these platforms demand being able to control the individual quantum bits in a scalable manner, because remember, we need to eventually scale this up to hundreds, thousands, millions. And you need to program them in some way. So there must be some inherent degree of programmability of these platforms. And today I'll focus here actually on the atom arrays. And there are many nice degrees of freedom that one can control with the atom arrays. So here, for instance, you can control the internal quantum states, the external motional states, You can arrange these arrays in different dimensions, right? 1 dimension, 2 dimensions, even 3 dimensions. And then they can be arranged in arbitrary geometries with user-defined doping, something that is not very easy to do in an actual solid-state system. And finally, you can also use lasers to induce tunable interactions over long range between these atoms. So in the last few years, atom arrays has actually really taken off as a platform of choice in the quantum physics community. And one of these key enabling techniques that allowed the atom array platform to become so popular was really this ability to control individual atoms in their optical traps by mapping the optical domain onto the radio frequency domain. So these are arrays of atoms that are trapped in individual tweezers, and the tweezers are formed from tightly focused laser beam. Now, if I want to have 100 tweezers, does that mean that then I have to build 100 different lasers? No. There is this magical device over here, for instance, that you can use, an acousto-optic deflector. And what that does is that it takes an incoming laser beam and it sends in a radio frequency wave, and it sort of kicks that laser beam off to one side at a given angle. So if you've got a given deflection, now that means that if you send in 100 simultaneous radio frequency waves, you can actually have 100 simultaneous deflections, which then get mapped onto the atom plane as 100 tweezers. So this is nice because all you have to do is to start off with a laser beam that's 100 times more powerful, which is much easier to achieve. So here you see an example actually of atoms, single atoms, in 400 traps, right, formed from 20 by 20 array. And that is the average fluorescence that you get. However, one problem is that if you have 100 traps, 400 traps, it doesn't guarantee you 400 atoms, because it turns out that the loading of single atoms into a tweezer is probabilistic. In fact, due to an understanding of atomic physics, that probability is about 50% or so. So the probability of loading a single atom into a tight trap is the same as getting a hit when you flip a fair coin. But now the problem comes in the following. When you perform your quantum simulation or your quantum computation, you have in mind a pristine atom array to begin with. So it should be defect-free, and you want to start off with 100 atoms. That means there should be no holes in between. However, as you can see, where you want to have 100 consecutive hits when you are given 100 coins, the probability of achieving that is really small. It's 0.5 to the power of 100, which is 10 to the minus 30. That's just abysmal. So we need a solution around this. And this can be done simply by starting with 200 coins, right? Flipping them and getting 200 hits, and then very quickly shuffling those hits together such that you have your subset defect-free array. So with this shuffling around of the atoms, okay, this can allow us to get a substantially higher probability of having defect-free arrays as a starting point for these quantum simulations. This can be done by simply overlapping a second set of mobile tweezers that pick up the atoms in real time and shuffle them. And real time basically means that this happens faster than a blink of an eye. So here you see a GIF image of actually 2 consecutive sequences, images that are taken of the atoms. So the first one is the initial loading, and you can see that there are many holes in between with the defects. And the second one, after tens of milliseconds, is your defect-free 225 atom array. And in fact, this defect-free array that you're looking at is pretty much one of the largest that you can get right now in the world. So going ahead, we've also demonstrated actually in our laboratory that we can apply this algorithm, rearrangement algorithm to various different arbitrary geometries. For instance, you've got the honeycomb, Kagome, link Kagome. These are all interesting for studying different advanced materials like graphene, and for studying superconductors or quantum spin liquids, like this Hilbert-Smithite crystal over here. We've also demonstrated that we can use this to potentially study fractals that are basically quite interesting as fractals occur in nature. And also just to show that we've done this in Singapore, we also rearranged this to form the lion head symbol with the single atoms. So as an outlook, here we are marching towards trying to understand advanced materials. So you can really now develop a microscopic detailed understanding of what is going on when you set up your spins to model a particular phenomena. Or actually now what is very hot in the atom array community is to use these atom arrays to tackle optimization problems such as these new classes of NP-hard problems like the maximum independence sets, which actually have direct applications in the placement of radio antennas for optimal network coverage, and so on. So with this, I kind of want to close by saying that, so far I've described using quantum physics to impact quantum computing and simulation. But there's really a range of quantum technologies, as Jenny mentioned in her introduction. There can be more precise quantum sensors that can be used based on quantum physics. And you can also use these for quantum communication, where the security is really guaranteed by the laws of quantum mechanics. So yeah, with this, I think I end my talk here, and I'm happy to take questions.
Thank you, Huanqian. So just to remind everyone who's joining from the Global Young Scientist Summit, you can send questions in through the event platforms and type them into Slido. So we'll be looking there and we'll put your questions. So Huanqian, maybe can you tell us a little bit about what's the next challenge for your research?
Yeah, so so far we have gone to realize basically one of the largest atom arrays. You can of course try to scale them up even further. Now that's not a straightforward task. There are sort of new architectures that might have to be developed, still involving lasers and atoms. But another direction now is to really try to induce interactions between the atoms that you have now generated, because these interactions are really the key to having some programmable features to be able to map them onto the desired equation that you want to solve, and try to understand models of quantum magnetism or other interesting aspects of materials. Yeah, I should also mention actually, in case anyone's interested, we also have a virtual lab tour to offer for our lab, so you can see what actually these experiments look like in real life.
Thanks, Huanqian. So although it looks rather simple when you show a picture of an array of atoms, I know from visiting your lab that you have a few large tables full of equipments, lasers and lenses. So you can look for the virtual tour of the National University of Singapore College of Humanities and Sciences to see a sort of 360-degree panorama of all the equipment that Huanqian's group has built up for these amazing experiments controlling single particles. I wonder, Huanqian, so you came to CQT in 2017, and that was when you were starting up your group with the NRF Fellowship. For young scientists in the audience, could you maybe tell a little bit about what was exciting and maybe what was challenging to make this transition to running your own lab?
Yeah, so I think it was really very exhilarating to be able to pursue my own research ideas. So these are ideas that you've sort of formulated over the years, and also they evolve as they go along. And it's nice that you're now able to chart every single thing out, right from deciding in your laboratory how it should be renovated, where the optical tables should be placed, to finally deciding what the atoms should be doing, what's the best transitions to address them, things like that. So I found all of that really exhilarating. And of course, it was really nice to be able to have the NRF Fellowship to back all of this up, to really transform the ideas that we had into actually, the physical setup. And it was also very exciting to be able to build a team. Sometimes I feel that, starting off as your own laboratory, it almost feels a little bit like starting a company, right? You have to find your own, you have to find funding, and you have to be able to talk to students and grow the people in your team. So all that was really very exciting, because every day there were just new things that had to be discovered in all sorts of aspects.
And you have how big is your group now? You have quite a few people working in this from different backgrounds.
Right, so we have 12 people in my group right now, split across 2 experiments. We're almost a little bit constrained by lab space, but the background that they have, it's quite diverse. There are people who, there's firstly in terms of educational background, there are people who already come with PhDs, postdocs, all the way to undergrads, whom we are very happy to take on and mentor. Many of them are physicists. So they come from a physics background, Not all of them start off with laboratory experience. Some of them even might be more interested in doing theory at the beginning, but then they want to try experiments. And also we've taken on engineers as well, who really come in with a very different perspective on how things could be built better. And building things robustly is really a part of our culture, because you need these atoms to be scalable and so on, and that does not work if things are always falling apart. So it was really nice to be able to tap on many different talents in the group.
Okay, well, I'm pleased to say that we have some very good science questions coming for you on Slido here. So there's maybe two that can be taken together. So one question is someone who says they're from biology. So how do you use these systems to study materials if the material aggregated into single atoms? And perhaps related, you'll be able to answer a question that's come from Edelman Jan in Switzerland, that how do you study the interactions between the atoms in the different tweezers?
Okay, so those are all great questions. So how we make the material is we really make a model of the material. So we're not claiming that the collection of single atoms that you work with, maybe if I pull up over here, an example over here, for instance, of the honeycomb, right? We're not saying that these honeycomb of atoms that we trap are exactly used for graphene. However, that's where physics comes in. Physics sort of distills the phenomena that is happening behind that has been observed with graphene, and we try to come up with models for those. And usually those models are the ones that then get input into computers to really solve exactly what are the dynamics of what is going on, and try to see whether that maps and that matches the experiment. But it turns out that some of these models, to be able to be solved exactly, are just very difficult, and it's too challenging for classical computers to take on. You can think of it as saying that there are too many parameters for the simulation to be able to handle. So this is where quantum simulation comes in. So we're not claiming that this is then going to be used as your graphene nanotube material that you take along with you in your pocket, but really this is allowing researchers to be able to develop more accurate models, such that now we can say, okay, with these particular properties, then that comes from these parts of the equation. Now, if you tune it in this way, what new things can we expect? And then we use those to hopefully guide the design of new materials that way. Yeah. So related to that, in terms of the interactions, so these are tweezer-trapped atoms, and we actually induce interactions between them by driving them to the Rydberg states. So Rydberg states are basically highly excited atoms. So you can think of sort of a very floppy atom, if you like, and that they can have a huge electric dipole moment, which then allows them to interact over large distances with a fairly high frequency. So just to put on some numbers, it's something like 100 megahertz kind of interaction strength, which is considered huge over a few microns. So with these Rydberg interactions, they're tunable. You can change the range of the interactions. If you drive two of them to Rydberg states, you can even have dipolar interactions between them. So in other words, they can be attractive or repulsive. Well, repulsive or attractive, depending on how they align relative to each other. And there have been many interesting things that have been discovered, and many more with these kinds of Rydberg atoms.
Okay, well, I hope this is answering the questions for the audience. We probably have time for one quick answer to one last short question. So V. Vijendran from Singapore says, when you scale up the optical setup for larger atoms array, does the computational cost of optimizing the experimental setup grow prohibitively? Maybe why, what's the limit on the size that you're dealing with?
Right, great question. So the computational limits of the possibility of using these arrays would basically scale exponentially. So it's rather the computational promise, is what I want to say. So if you really could realize, 1,000 atoms instead of 100 atoms, well, that would basically be, e to the 10 times more higher computational power that you would get. So that is very promising for tackling those very complex problems and so on. But in terms of building the setup, the beautiful thing is that you do not need that much more to be able to scale up, precisely because of some of these devices that I've talked about previously, where you're really mapping the optical problem into a radio frequency problem. And so because the frequency has come down by so much, it is much easier to control. And in a way, to some sometimes you might be limited by the bandwidth, but you can always also stack them in different dimensions, which also allows you to scale up quite significantly. Yeah.
Okay, thank you. I'm afraid we're going to have to end our session here with so that we can return the GYSS participants to the live audience. For those, if we didn't get to your question, or if you had questions you didn't get a chance to ask today, please look us up online. So CQT is Quantum Law on the web and on social media, and Huanqian, you'll be able to find a group page there too. So yeah, thank you, Huanqian, for the talk. Thanks, NRF, for inviting us, and thank you to the audience for listening.
Yeah, thanks to everyone.